All right, welcome to this symposium presentation for the online edition of the Conference on Computer and Robot Vision 2020. My name is Francois Pomerleau, and today I will talk about autonomous exploration related to subterranean and subarctic environments. As a short bio, I'm working in robotics for more than 10 years now. Most of my robotic expertise come from deployment in Europe, mainly Switzerland, Germany, Italy, and the Netherlands. And the key application I work on were mostly search and rescue, inspection, environmental monitoring, healthcare support, and so on. I had the chance to use robots in many locations, such as city streets, pre-alpine lakes, underground metro station, houses, open pit mine, and military training sites. And here you can see a couple of those field deployment I had the chance to do in the latest years. But for now, I started 2 years ago as an assistant professor at Laval University, where I am the director of the Northern Robotics Laboratory. Where we tend to specialize on is mainly navigation algorithms, heavily based on LiDAR, with a special attention to having a validation in real life conditions. So, in other terms, we train field roboticists. We do a lot of 3D perception, which include artificial intelligence, and lately we started a trust on research on control. So within those fields, our main focus, we do a bit of sequence detection, a lot of localization and mapping, a bit of path planning, and recently a bit of path following and control. So for this talk, we'll use two main applications, mainly subterranean exploration, where communication with the base station, thus water traversability, are currently open challenges. And also, I will finish with a bit of subarctic exploration, where cold, storms, unstructured environment caused by forest and snow, and mainly the scale of the environment are still open challenges. Let's start with our participation to the DARPA Subterranean Challenge, so in short, SUBT, and let's see what's going on there. So a bit of history on the DARPA challenges for those who doesn't know yet. DARPA is organizing a lot of challenges. Four of them were related to robotics. The first one in 2004 2005 was the Grand Challenge, where autonomous car had to travel 212 kilometers in the desert. In 2007, there were the Urban Challenge, where there was mainly city street and roughly close to 100 kilometers of urban area that had to be completed within less than 6 hours. More recently, 2013, 2015, there was the Robotic Challenge, which focused on disaster and emergency response scenarios with tasks such as, so it was a humanoid, and the humanoid had to drive a vehicle, travel across rubble, remove debris, open doors, and so on. And what remained is the Subterranean Challenge, which started in 2017, and this is the one I will talk about in more details. So what is that challenge? First off, there is, of course, a 5 million cash prize. And the task is to have a fleet of robots and to be able to map, navigate, and search in different subterranean environments. They focus on three type of environment, so namely tunnels, which would look like mostly mines, urban underground environment, which could be metro stations or nuclear power plant, and so on, and cave, so natural environment that would be more unstructured than the tunnel version. So in 2019, October, there was the first trial, the first competition in a safety research coal mine in Pittsburgh. And then recently, February 2020, we finished the urban challenge, which was in an unfinished nuclear power plant in Elma, Washington. And we're given COVID-19 crisis, we're waiting for the location and the date for the third installment of the challenge, which will be in a cave. So up to now, we still don't know where that will be. And at the end of all that, there will be, let's say, the grand finale, which should have part of all of those three environments in the same location, and where the team will compete for the final 2 million cash prize. Currently, the key teams participating in the Subterranean Challenge involve a lot of high-level university or even research centers such as GPL, Caltech, MIT, KAIST, CMU, ETH, Oxford, Berkeley, and so on. And in those list of teams, Laval University is part of CTU CRAS NORLAB, which, as far as I know, is the first time a Canadian university is officially registered in any of the DARPA challenge. So that's something I'm quite happy of. And here's our team. This photo was taken during the urban challenge, and we see our fleet of robots, which for that configuration there was one husky, so the yellow one, three, I will call them trader robots. Those are tracks vehicle with wide tracks behind. Those are actually very old robots. I did my PhD on them, so they are maybe 12 years old now. There was two flying vehicles, namely Flame Wheel F450 from DJI, and three hexapod robots that were custom built by one of our colleagues in CTU in Czech Republic. So how to win that challenge? Only one operator can interact with the fleet of robots. He can be held by a pit crew of a maximum of 10 persons, and those 10 persons can interact with the robot only if the robots are in the staging area, where each team has 30 minutes to set up everything, including the the base station, aligning the robot, and so on. Then the operator has 60 minutes, so an hour, to report 20 artifacts in an unseen environment. To gain a point, an artifact must be reported within 5 meters radius accuracy, and the ground truth is given by DARPA. The main artifacts that we had for urban, so the artifacts change depending of the location. There's a common set of artifact, but for the urban environment, we had to find mannequins which were actively heated, and they were wearing reflective jacket and hats. There was a red backpack, air vent, and those air vents were also actively heated. There was a cell phones to find with Bluetooth, Wi-Fi, and they were making sound, and the display was on, so there was many way to detect those cell phones. And also they had the CO2 gas leak, so those had to be detected with a specialized sensor, because there was no clear visual way to identify those gas leak. How those detection happen? There was a small staircase which would actually go down for 3 floors, which was not that easy to navigate in. And eventually, at the end of this staircase, we could report a backpack. So we used a modification of YOLO for the artifact detection in the images, which is the case for most of the teams as far as I know. And then the exploration go on for a while. There was two cores which were around a nuclear reactor. So here we can see the type of maps that we did in blue. So in the alpha course, our team managed to score 4 points at the first trial, and then only 6 points. So we see the location in blue that we could explore. And on the right side of the figure, that's the ground truth that DARPA measure with theodolite, so fixed tripod, to measure all of the environment and the artifact locations. On the beta course, it was a bit harder to navigate actually in the all area. The all stage started with a very long hallway, and then we had to cross that, and then a lot of artifacts were towards the end of that long hallway, and we see how little actually we managed to explore when we compare to the full map or the full area that DARPA installed for us. And by the way, those maps were realized only by the Husky. They are not the fusion of all of the platform. And the way the scoring was working is that they would take the max of alpha cores plus the max of beta cores. So in that case, we managed to score 10 points in total. That being said, we can talk about lesson learned, which is mainly stuff that breaks and that we typically don't report on in articles. So I will use the opportunity of that presentation to give you some insight of what happened. We only had limited footage on the situation inside, so I will try to do my best with the video recorded directly by our robots. So the first lesson learned is that flying is hard, especially when you have low bandwidth and you don't control much. I'm not sure if you have seen in the middle of the video, but after 12 minutes of autonomous flight, which was the longest time any teams managed to fly, there was a hardware failure, and then the drone smashed in the concrete wall, and the rest is smoke and fire extinguisher, essentially. So at the end, we finished with a totally burned Quadrator, but for whatever reason, the Ooster managed to survive the crash and the fire. Also, unfortunately, none of our drone managed to came back with data. So given the low bandwidth and computing power, the strategy was the drone would be deployed and then come back to the station to report any artifacts. But at the end, only one burned, but a lot of them got stuck in multiple places. So here we see the staff from DARPA taking out our drone somewhere safer. Second lesson learned that you should be creative. Here we had the husky that got stuck on a small concrete wall, a bit like a turtle stuck on its back. And the operator decided to use one of the track vehicle to just kick it. And took quite some effort to get it out of there. But eventually we managed to pull it out. And the good thing about that is that the husky could continue and actually manage to score more artifacts. And here we see the husky back on his wheel, and will eventually continue to explore. Another lesson learned is that you can have surprise when you push the hardware to their limits. Here we can see in the sequence of videos that there is a brick wall that is about 40 centimeter high. It's not a brick wall, it's a pile of bricks that were there. We knew that most probably there was something on the other side. So the husky doesn't have a high clearance on his wheel. Nonetheless, the operator decided to just go back and go full speed in the brick wall. And with a lot of surprise from the team, essentially the robot managed to go over the wall and continue exploring. Another thing, in here I will have you focus on the small video at the lower part of the screen. Be careful about hardware modifications. Over the year, the trader robots, so the track robot, were heavily modified and the battery was moved at the back. So on one of the staircase, the center of gravity of the robot was not well and was not where we thought, and eventually the robot tipped over completely. So the second thing is that you should be ready to quickly repair your robots with whatever you can find locally. And here the good thing of having those very old robots is that the team knew how to repair them very, very rapidly. Finally, don't underestimate mission integration tests. So you should be used to unit tests and then system tests, but once you deploy a lot of robots together, it starts to be a bit more complicated. So here the hexapod was used to just boost the data transmission to the base station, but eventually the trader robot saw that as a manageable obstacle, so just decided to move over it. So again, be ready to repair and replace efficiently. So at the end, I'm quite happy about the results. We actually, for the second time, we finished third over all the teams, but mostly we finished first as a self-funded team. So teams that were funded by DARPA receive around $1 million US for the first year of participation. and are expected to receive another $1 million for the second year. So that gives a scale of the investment that is required to participate to such a challenge. And in that case, the good thing is that we still receive $500,000 to continue to work on the challenge. So very rapidly, I want to talk about LiDAR-based mapping in winter condition, which is the current research that we are doing, where there's many application in subarctic environment for our research, and the first one is remote inspection of major infrastructure such as road, dam, power line, and so on. So as opposed to urban navigation, where it makes sense to have multiple engineers to maintain an accurate metric and semantic map of the city, remote location are visited only few times, putting a lot of pressure on the robustness of the SLAM algorithm that you deploy. So here we see an example what they have to do to inspect power lines in Quebec City. Second application is the forestry industry, where a lot of activity happen during winter to avoid ground sinkage. So on top of the environmental challenge that I named before, there's the perception needs to be robust to outlier caused by tons of debris and all sort of particles that are flying through the airs with those machineries. And finally, moving from subarctic to Arctic, there's a lot of fundamental research to be supported related to environmental monitoring and climate changes. By using robots to automatize the data collection, we can augment spatial temporal resolution of those models generated by field researchers such as ecologists and biologists and geologists. So we try actively to support those people. For most of those tasks, we focus our attention on maintaining consistent large-scale map of the environment. So here we have a map that is roughly 300 meter by 200 meter on the campus. And we aim at real-time localization with low drift to reduce reliance on loop closure. Because what we discovered is that on most of the field deployment, it's actually quite hard to force loop closure. Usually tend to go on a very long path for a while. So for registration, the main tools that we use to build our 3D maps is Le Point Matcher, which is open source software that you can find on GitHub with an extensive documentation. So if you're looking for something to do point cloud registration, take the time to have a look there. One example of recent research we had is simply to add some penalties on the input to reduce the drift of large scale map. And here again, we are field hypothesis. So people, the researcher had to do some actually had particular obstacles to go through, mainly snowfall, weird obstacles on the path. We even had to stop and turn back because of wildlife around. When I'm talking about large scale, we see here the type of map that we did, again, without relying on loop closure algorithm. So the total path length of those three maps is 4.1 kilometer. And the tiny inset on the side give you an idea of the scale of the map. As a follow-up to this talk, I invite you to have a look at Dominique Barry's talk on session 5. He will present a great paper, and you should be able to discover what's the main difference of try to estimate the motion of a tank-like vehicle, whether it is on concrete or in snow. So that should be quite interesting. You should have a look. Hopefully this talk teases your curiosity on field robotics. If you have any questions, don't hesitate to write to me. If you want to receive some updates on our results, you can follow us on our many social medias. And on that, thank you for watching.